All right, here's number 13. Calculate the escape velocity from Venus given the mass of Venus in kilograms, the radius of Venus in kilometers. Of course, we already know that the radius has to be in meters. So it's 6051.8 kilometers. 1 kilometer is 10 to the third meters. The kilometers cancel. So this is, sorry, 6. That's supposed to be a 6. 6051.8 times 10 to the third meters. All right, so that's the number I'm going to use. Here's the escape velocity equation is the square root of 2gm over r. All right, so it's going to be the square root of, exactly like the last one, 2 times 6.67 times 10 to the minus 11th. Right, the universal gravitational constant times the mass, which is 4.87. Remember, it's virtually it's almost the twin of Earth, right? At least in mass and size, times 10 to the 24th. So the escape velocity should be very similar. Keep in mind for the Earth, it's about 11.5 kilometers per second. All right, anyhow, let's just do this one. 6051.8. Remember, this is the average radius of the planet times 10 to the third. Of course, that's got to be meters. Anyhow, I didn't have to put the meter thing in there. So let's do this calculation. All right, here we go. All right, so all right, that was the one for Mercury. Let's clear this. All right, so here, let me move this. All right, I'll move it to right here. So we're going to do what's underneath this square root because that's the way this calculator works best. So it's 2 times 6.67 times 10 to the minus 11th. All right, and then times the mass of Venus, which is 4.87 times 10 to the 24th, divided by 6051.8 times 10 to the third. All right, so this is going to be what's underneath the radical. All right, and then we take the square root of that, and the answer comes out in meters per second, right? So, it's going to be something around 11,000 meters per second. All right, so we're going to take the square root. All right, so this one comes out to be 10,360.9, whatever, right? But this says it says to calculate it in kilometers per second and round to one place past the decimal. All right, so kilometers per second, this would be 10.3 kilometers per second. All right, so that's the answer, 10.3. All right, let's move on to number 14. All right, just like we did for Mercury and Venus, we're going to now do Mars. The escape velocity, of course, we already know that the radius has to be in meters. So here's the average radius of Mars is 3389.5 kilometers. Actually, let me say something about this real quickly. One of your homework questions is to figure out what the escape velocity would be from 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 this radius. This is the average radius of the planet Mars. The average height, if you will, of the planet Mars from the center. And then if you were to be asked, okay, well, what is this escape velocity? All right, so let's say if it's a different problem from the top of Mount Olympus, right? Sorry, Olympus Mons, which is the way you're supposed to say it. Just keep in mind, so you have, this is the radius, and then Olympus Mons, goes up. It's kind of like a volcano looking thing. Anyhow, if you know what the height of Olympus Mons is, which is about 25 kilometers, so what you would do is you'd say, okay, what is the height? What is the distance from the center of the planet? So you would use R plus H, okay, in your calculation. All right, so this one, we're going to do. Here, I'll do both examples just for the heck of it. All right, so the escape velocity from the surface of Mars, right, is just to convert this, you just change it to times 10 to the third, right? All right, so you can play this little game. 1 kilometer is 10 to the third meters, right? So the kilometers cancel. All right, so anyhow, the escape velocity is going to equal the square root of 2 times big G, which is 6.67 times 10 to the minus 11th times the mass of Mars, which is 6.4 times 10 to the 23rd. All right, and then divided by, okay, so this is the only difference between, where you do it from the surface or you do it from the top of Mount Olympus. Okay, so it would be 3389.5 times 10 to the third. All right, so it's the exact same equation, but from the top of Mount Mars. So this is the top of this mountain. Okay, so that's not drawn exactly right. So from the top of the mountain, the escape velocity would be, I gotta do a quick calculation here. Where's my calculator? All right, there it is. All right, so what I would do is I'd just say, 25 plus the average radius of Mars, which is 3389.5. Right, so I'd add those two together, right, and so and then of course change it to, add times 10 to the third. So the escape velocity from the top of Mount from the top of Mount Olympus, or Olympus Mons as it's called, would be it's the same numbers, okay, or just about the same number. Square root of 2 times big G, which is 6.67 times 10 to the minus 11th, right, times the mass of Mars, which is 6.4 times 10 to the 23rd. That's supposed to be an E, sorry. And then now divided by, so when you add the height of Mount Olympus, where is it? The height of Mount Olympus to the height of the average radius of Mars, it's 3414.5. So 3414.5 times 10 to the third. All right. So what we're going to find is it's going to be a little bit less from the top of Mount Olympus. You don't have to. You've already lifted it 25 kilometers above the surface, so you don't have to spend as much energy, which translates to the escape velocity, right? It takes a smaller escape velocity to leave from Mount Olympus than it does to leave from the surface, from the average the average distance that the planet is from the surface is from its center. All right. So anyhow, let's do both these calculations. We got time to do that. All right. So all right. Well, see, since I already got this one in here, I'd say so that number. Let's see. Can I do this? Exp to the third equals. Now, all right. Here, I just got to redo it. Okay, so it's going to be 2 times 6.67 times 10 e to the minus 11th. All right, I'm going to do a little shortcut here. Times 6.4. Oops, 6 point. Here. How do I do that? 6 point. Shoot, 6.4 times 10 to the 23rd equals. Okay. So now, see, that's the numerator of this. Notice the numerator is the same with both of these. So I'm going to store that just to make my life a little simpler. And then I'm going to, for this one, I'm going to divide by 3389. So divided by 3389. Oh, shoot. Go back. Oh, just go back like that. 3389. 3389.5. I'm doing this one times 10 to the third. E to the third. All right. So this is with what's underneath the square root. So then I take the square root of that. All right, and so that's the escape velocity from the surface of Mars, right? So if I divide that by 1,000, it would become, it's just 5 kilometers per second. All right, so this would be 5.0, right? Because it tells me to round one place past the decimal. 5.0 kilometers per second. All right, so let's do this one on this side. Okay, so remember I already stored the numerator of this, so that's going to make my life a little bit simpler. All right, so here, let's clear that. So so the numerator is that, and then divided by the distance from the center to Mount Olympus, which is going to be 3.4, the top of Mount Olympus, 14.5 times 10 to the third, right? 10 to the third equals, all right, and then I take this, so then I take the square root of that, all right, and see, I get, it's a little bit small, yeah, it's not much smaller, because compared to the thousands of kilometers to the center of Mars, you can see it's a little bit different than the other one. If I had done it in meters, you would have, you could see, it's almost exactly 5. So in kilometers, it looks basically the same. It's just slightly 0.0 kilometers per second. So it's just slightly different, slightly smaller. All right. So anyhow, yeah, I should have just done both of them in meters, and then you'd see it's a little bit larger from the ground as it is compared to at the top of Mount Olympus, or Olympus Mons. I keep saying Mount Olympus, but you're supposed to say it in Latin, which is Olympus Mons. All right. Anyhow, let's go on to the next problem.